Okay, good morning, everybody. Let's start the program of Tuesday. We will have the second lecture by Alexander Zhiboedov, and he will continue with the topic of gravitational as matrix scattering. Please, Sasha.
Thank you. Yesterday we started discussing universal aspects of gravitational scattering at high energies, and today we will continue doing that. So let me recap what we've been saying yesterday, and we argue that the natural space to consider, well, there are several of them, but one is the energy of the process, and the second is the impact parameter. And we identify several regions in this space. One, depending on how impact parameter scales with energy. Here, the scattering was really weak. It means that here you can apply tree level. Then we found this one here, which is the classical criterion for collapse. And here we expect that when we scatter particles, the gravity becomes strong, and scattering is highly inelastic. Notice that even though you can talk about classical collapse, but because we are talking about 2-to-2 scattering amplitude, the process is highly quantum, because then the black holes have to decay into two particles. So we haven't talked about much about this region yet. Then we identified a couple of other mechanisms where inelasticity kicks in. So one was tidal, and another one was gravity waves, and I missed a factor of 2 here yesterday, if I remember correctly. Maybe not. And finally, there was this observation, which was important, that we can go beyond this weak region and we can have an iconal scattering, an iconal saddle point, which scale as 1 over d minus 3 log s. So this was the picture, and the formulas attached to this picture were as follows, that we consider scattering in the impact parameter space, and here we can write it as 2I delta minus 1, this phase shift. Then we discussed that on the iconal saddle, which we can compute, the amplitude behaved as 2 minus d minus 4 to d minus 3. And the important point was that this ACV saddle was located at Q, which is related to T equal minus Q squared, at Q equal G Newton S times B d minus 3. So, and in particular, from this we concluded and conjectured that this iconal saddle point controls the Regge limit. But we also discussed that in this region, our control of what's happening is less. Well, here there is no control, and here there is some expectation or some picture proposed by Matti, Cefaloni, and Veneziano, but it would be good to test it. So now I want to comment on draw another line on this plot, which is our next step. Yes, and the conjecture was that this amplitude controls the Regge limit, and so now you can ask, what about the fixed angle? again, I will just do this computation. So fixed angle, at fixed angle, and high energies, let me take angle to be fixed and small. We have theta order 2q over square root s. So this is simply follow from definition of the exchange momentum. And then if you plug this formula into this saddle point equation, you get this famous formula. So let me take it to be small first. That at fixed angle, the saddle point is located at the following relation. So in particular, you see that if we consider, say, small angles, then the impact parameters which are supposed to dominate are much larger than the Schwarzschild radius. However, they are expected to be in this regime, so they are shifted by some constant from this collapse region. And so here we expect to have fixed angles. And in particular, because you see that at this point already tidal excitations and gravitational wave are produced, you expect the scattering to be highly inelastic. So let me estimate again. Yeah.
Yeah. So you're just taking the same saddle point that you use for the Reggie limit.
Yes.
And you just
yes. The idea is that let's first take S to be small enough so that these effects are small and we're sitting on the saddle, and now we're increasing S, and then increase S as we discussed. This becomes big, but still the phase is very big. So I'm taking the same saddle. Yeah, it's questionable.
Okay.
I agree. But I want to still do that because I think some things that people do are even more questionable. So I thought this is sort of a safe wave to a formula that I would like to write. And let me do it. I told you that this estimate of production of gravity waves from the simplest diagram was given by this formula. And now if you evaluate this on this ACV saddle, you get, you can check that. If you plug in B this ACV saddle, what you get is a black hole entropy times the angle 3D minus 10. And in this way, notice that the physics here, the expected physics, is, even though maybe we cannot compute it with the gravity wave, but the expected physics at the fixed angles, is the impact parameter is still much larger than the collapse, so the black hole physics is irrelevant. So this black hole entropy has nothing to do with black hole. It's just the outcome of the computation, but there is this conjecture in the literature which is, I would say, very hard to justify, but let me just present it. And the conjecture is sometimes people say that high energy fixed angle in gravity is that T S theta is proportional to e to the minus s black hole square root s times f of theta. And at small angles, this is again the picture of ACV, that at small angles this function behaves as theta 3D minus 10 up to log theta, which it's a subtle story, but there could be extra logarithm here. So this is another formula that people like to write in this subject. There are various words produced, but it's hard to compute, of course, and so let me just present it as is. And it expresses this, and this function f at small angles, as I said again, we expect the physics to be related to production of gravity waves, and it seems like a nice target for possible, well, I don't know, Bootstrap, not Bootstrap, but at least it's a region which seems to be far away from the collapse, so that maybe we can understand by gravity waves, and that's in fact what people have been trying to do. So it seems like a nice target to fix the leading small angle behavior of this function. Okay, now I would like to, so this is, I think, yes, and maybe I make last comments. So you can ask, it seems from what I'm saying is that at small angles, the scattering is highly suppressed. There is a black hole entropy suppression, and then you go through collapse region. What happens? What's the difference when we switch to the physics of gravity wave production to the collapse? Because in this formula that I wrote, well, if we believe this formula, then this function f of theta, it starts small, and then it grows to order 1, say, with all the words about possible smearing, etc. And I think one sort of proposal, again, or picture that people have, which again is not hard to justify sometimes, but there is some sense in which when you cross this collapse region, perhaps there is a transition in the behavior of the phase of the amplitude. So we can, if we write the amplitude as a t times some phase, I told you that there is a suppression of the absolute value, but you can ask what is the behavior of this phase. And at least here, in a sense, when the scattering is almost elastic, there is a large phase, but it's smooth, it's computable. So it is, in some sense, it's integrable. It's a smooth phase. Whereas in the collapse region, it is expected that the phase become chaotic because black hole is like many, many resonances which are long-lived, and there is this some words. It would be nice to make them precise, but somehow that this transition perhaps is not in the absolute value, but maybe in the phase in some sense where this phase is chaotic and this is somehow integrable. But again, I'm just presenting the physical picture here. And I think these are the things that follow just from general considerations and the arguments which do not care about the specific UV completion, but also seem to be quite universal.
So Sasha, can I ask?
Yeah.
Sorry, just a basic question. So there are two sources of ignorance. One is in finding this plot as a function of B and S, and the other as translating from B to angle, right?
Yeah.
So things are a little bit less unclear in this plane, right? In B and S. It is when you try to also translate to angles that sometimes you are not sure which regions of this plane contribute. Is it?
Yeah. I think that's so. I think that this plane is simpler. The angle plane is trickier because the angle plane. I think the basic point that people understood at the angle plane is that when you fix angles and you take high energy limit, you always ends up. You see that if you approach it from low energies, you're approaching along this line, and you see that all these effects become big, and so you don't know exactly what. So in some sense, fixed angle is more complicated. And you see that if you approach from low energies, these effects are small, and then the amplitudes start becoming suppressed. And I think the basic physical picture, which makes sense to me, is that we are doing 2 to 2. Energy grows, we produce more waves, more strings, and so the amplitude just gets very small. And then if you evaluate on this effect, indeed, well, you see that it becomes small, but how exactly small it becomes, that's a tricky, because if we have something very small, of course we should worry about what about tails of the wave packet, and people make some arguments again that tail of wave packet is irrelevant, but yeah.
And the energy spin plane is roughly.
I will talk about it because I think for Bootstrap we like energy spin plane and we want to work there. But I think to talk about energy spin plane, we also want on this axis to put some numbers, right? So that it doesn't just go asymptotic, and so that's what I will do next.
Okay.
Just to go all the way to 0 and here to have j. So this would be the goal.
Nice.
But yeah. Let me now, this we derived say from some gravitational pictures. So let me now do some simple Bootstrap P analysis with this. To this, I will, as I said, I will assume that amplitudes satisfy all the basic properties we like. In particular, I will assume that it obeys unitarity, so we can write a partial wave expansion and see what we can do with that. And well, let me write in some form. These are some Legendre polynomials. And now we can introduce partial waves in the spin plane that Pedro just mentioned. So it is 1 for no scattering and plus 1 plus I. In my convention, it will be S 4m squared if you want, d minus 3 over 2 square root S f of j. And the unitarity is simply the statement that S of j of S is less or equals than 1 for S positive. So that's what we want. So now let me add this and use. Yeah, it depends if you want to have external guys massive or massless. That's true. Yeah. Thank you. Now I want to derive. So I told you that there is a conjecture. There is a conjecture that this iconal amplitude controls the radial limit, and therefore the radial limit is like this. But for this, we would like to make sure that nothing else spoils it. Because you can wonder, okay, here we do not have control over the amplitude. How do you know that all this physics which we don't control does not spoil this iconal? So let me just do this quick argument that how we do that. And the argument is the same as the one you use in the derivation of the Froissart bound. Basically what you do is, yeah, sorry, let me, before going this, just to make some comment which, so if you are not familiar, so that you know that in d larger than 7, d larger equals than 7, the partial wave converges absolutely. In, say, d equal 6 and 7, well, if you define this, if you truncate this sum and take the limit, it exists. In d equal 5 and 4, partial waves does not converge. So it converges in the sense of distributions, as I guess described by also recently by Jashin, Peter, and Slava. And in particular, so something that you can use with partial waves is that you can define this smeared amplitudes as first discussed recently by Dali, Mill, Simon, David, and Leonardo. This is for gravity. It doesn't matter because all this convergence, all these convergence properties. So okay, it does matter if you have an amplitude where you exchange a graviton. So it could be AA, BB. So then the large J is controlled by the graviton exchange, and so convergence of the sum is controlled by the graviton, and so any gravitational amplitude will have these properties.
Okay.
If you don't exchange gravitons, then yes, then I don't know. And so you can also, to improve situation here, or in general, you can consider this smeared amplitudes, where...
But, sorry, can you say a bit more about this convergence stuff?
Okay, sure. So what you do is simply this. So remember that if you want to discuss this convergence at fixed S, you are going in this direction. So you always end up in the weak regime, so you can use the tree-level phase shift. So then what you have to do is you simply take the sum. This behaves as GA to the D minus 3. This is bounded by some power of S. In my conventions, 2 maybe minus D over 2. And for Legenders, you can use also some bound. I will write it. And then you just see that if you, for f of G, you use this tree-level phase shift, which is large G is controlled by large B. So you plug tree-level phase shift, and so then you have a sum at large J, which you can just look at it, and then you see if it converges or not.
And that's just to reproduce the 1 over T pole in the...
Yes, it's just 1 over T pole, yeah. Well, I simply say that if you define partial sums, then and take the limit as J max goes to infinity, it's convergent. So it's not absolutely convergent. No. Yeah. And last point, which is also related to some physics, which is that you can define this smearing over momenta from 0 to Q naught, and people use it in dispersion relations. And so absolutely convergent means that you're allowed to put here an absolute value. So then, if you put an absolute value in D larger than 7, it's still convergent. In D5 and 6, because we're at negative T, so Legenders oscillate, and it helps you. As far as I would say, not really, because in fact, well, this point-like amplitudes, we use it all the time, but they're not very physical. In physics, we always have to smear over S and T, and I think this washes out all these very fine features. So. At least I'm not sure. The only dramatic difference is D equal 4, of course, but there we don't know. Now, another thing to know is that if you do the smearing and you choose your smearing function to vanish close to 0 and to vanish, it's just I define some class of smearing functions that vanish close to the regions. And you do this. This is the effect of this is to suppress large spin. And again, the intuition is simply that if you smear Legendre polynomials close to 1 because they oscillate, it is able to dump it, and then by increasing A, you suppresses the contribution of Legendre close to 1, and okay, here you also need to have enough smoothness, and basically you can check that if you take a Legendre polynomial and you integrate with such functions, then you suppress large J. And large J is the same as large B, of course, large impact parameter. So in general, the intuition is that when you do the smearings, if you want to get rid of the large J physics, for example, you find it boring, that's what you can do. Okay, now let me do this simple Froissart-like argument where I take my model for the amplitude, and we simply split it into some J star and J star to infinity. So this is sum of partial waves. And here we can use some known physics, which could be, say, iconal physics. that we are happy about. And here, we can use non-perturbative unitarity. So you basically just take the sum and you majorize it by using non-perturbative unitarity here and using the properties of Legendre polynomials. So this is the exercise we try to do carefully with Kellyan, and say for the iconal model, you take all these unknown regions of collapse and gravity waves, and you see that at large S, it produces the effect S2 minus D minus 3, say 2, D minus 2. And to remind you again, here from the iconal physics, we got S2 minus D minus 4 to D minus 3. And so you see that this physics dominate, and therefore it makes sense to trust it. Because just by non-perturbative unitarity, we see all the physics that we don't understand is subleading. So in this way, we can now play this argument where we draw the S-plane and we use unitarity here to bound the amplitude. We use crossing here. And we assume that the amplitude is sub-exponential here. And in this way, we now can derive a bound on the amplitude, not just on the real axis using this iconal, but everywhere in the complex plane. There are various subtleties with that. Basically, so I told you that in 5 dimensions, gravity waves kick in earlier than tidal. Then, well, you sometimes have to smear. But I think the basic punchline is that, let me write that there is a Regge bound. On the amplitude, if you do pointwise, it's S2 minus D minus 4 to D minus 3. And as I said, this we believe is saturated, so it's optimal. And if you do smeared, and again, you play the same game of bounding Legendres, which are smeared Legendres, you get S2 minus min 1 A D minus 4 B plus D minus 1 over 2 D minus 2. So let me just comment. Here the most important point is that this guy leads to this fact that this is 0 pointwise. And here you see that, and I think this was pointed out in the paper by Leonardo et al., is that since this comes from large J physics, and I told you that smearing suppresses the large J physics, you expect that by smearing you should improve the bound. And you see that here that's the content of this formula. Remember, this A and B were defined as properties of the smearing function, so it should be smooth enough close to the origin and some factor Q0. So if you make A and B large enough, you see that you can bound the amplitude as S. So with enough smearing. So when A is larger than D minus 4 and this is larger than D minus 2. So that's a basic picture. Now that we have these properties where we combine the non-perturbative unitarity and basic gravity, we can test it in some non-trivial way, and there is a neat test we can do, which is let's write now twice subtracted dispersion relation. And if we write twice subtracted dispersion relation, we then can have an amplitude as usual, amplitude at low energies expressed through the discontinuity on the cut. So let me write it like this, the T as T, and here, all right, 2 pi. I will be a bit, the formula will become precise very soon, but this is the rough formula where we, in principle, we combine S and U channel cuts, and it's a twice subtracted dispersion relation. And maybe you do not recognize some of the well, there is a usual denominator, but the point is I want to make is that here we have an amplitude, here we have a discontinuity. This factor of 2 is crossing. The fact that we do not have arc, we use a Reggie bound, so there is a lot of this information which we believe in Bootstrap was put in. But now we learned from GR by doing 2 different computations the following fact. Let's take t equals 0 in this formula. As we take t equals 0 in this formula, as I told you, the first fact is that sorry, S is here, yeah. So if I take t to 0, here we know what we get. This is 8 pi g Newton over, say, t, the minus sign. And here we get the integral, and in fact, as we know, the only way you can get a pole is from the Reggie limit, so we can cut off it at arbitrarily S naught. So now this is a precise formula with all the factors, which just follows from twice subtracted dispersion relation in gravity when we take t to 0. And in principle, you see there is S naught, which means that I can chop it at some S naught here, or there will be some cuts, but none of these cuts have a pole. So therefore, they're all subleading. They're all subleading in this formula. And if I focus on the pole, this is the right formula. But now the interesting thing is that, so this is a sort of Newton's potential. And this is, as we agreed, this is, we computed at high energies as a propagation through the shock. And it's very much possible because consider the following formula. A simple example. This will not be relevant, but consider the following formula. S prime 2 minus alpha prime t. Plug it in this formula. The pole does not depend on S naught. It's not an equal sign. I can put 3 dots. I can put some dots here on the left-hand side, but as I try to say again, so this is a statement about the pole. This is a statement about the pole. And again, you can turn it into a rigorous Tauberian theorem, but I'm doing something more direct.
But why is it not that at every S prime, as t goes to 0 in your first equation? So you fix S prime, you send t to 0, why doesn't the integrand just develop a pole for every S prime?
Sorry, say again?
Why doesn't the integrand ts just develop a pole for every S prime? Because it's the discontinuity? Is that?
Yes, discontinuity, yeah, it doesn't have a pole. The discontinuity does not have a pole. So what we've done here is that we use dispersion relation to express this potential through the propagation through the shock wave. And as far as I know, in classical GR, we do not have such a relationship. So it seems like it's a non-trivial test if this is true or not of all our assumptions. And so let's just plug what we get on the iconal saddle here. So this is an iconal saddle. And see if it holds. And well, it's a nice exercise to do. You basically write the discontinuity as the integral over 2s 2 pi d minus 2 over 2 infinity db bd minus 3. This is the integral over impact parameters qb 4 minus d over 2. So let's just write it. D minus 4 over 2 dq. And here you plug this sine square of the tree-level phase shift that we computed by first lecture. Now you plug this formula. You plug this formula here. You do the integral over s prime. You get a neat integral of this type dx over x squared sine square x, which 0 to infinity, which evaluates, if I'm not mistaken, to pi over 2. And you plug it into the dispersion relation, and basically the basic result is that it checks. It checks, and therefore it seems like it's a sign that quantum gravity might exist, because it seems like it's a consistent. We got a consistent picture. Notice that this factor of 2 knows about crossing, and this was two independent computation in classical GR. So now maybe someone knows a quick way of why these two are related, but to me, I only know how to check it by doing the computation. Because a priori, you have the sine square, you have this very high energy process here, you have this pole, and it's consistent. Now, of course, it's an interesting question if there is a. So yeah, we tested this with Kellyan, but in principle, you might ask if there is a generalization to gravitational loops, which should also presumably have a universal part. I don't know. I haven't seen this done, but recently there was this paper by Simon and co-author, who unfortunately I don't remember, where they did similar test for string amplitudes, for stringy loops. And there they showed how it works at a one-loop order. So perhaps there is a similar story for the gravitational iconal to be understood, where we should be able to perhaps continue this game. But I just wanted to emphasize that sometimes people write these formulas that the Regge limit in gravity is just some simple power. I don't think it's as we looked at the iconal, it's not a simple power. It's a complicated function with a complicated phase, and it's totally consistent with the sum rule. You don't need some simple power to get this pole. If you look at this integral here, this x was defined. We were integrating over impact parameter. This x was defined by this parameter, and indeed, so this corresponds to when x is of order 1. This is a tree-level phase of order 1. So it probes this regime where it is of order 1. So this was a nice, simple bootstrap check of this general picture, which suggests that, at least in this iconal regime, it's all consistent. Now,
so sorry.
Yeah.
From a diagrammatic perspective, iconal is you're resumming some diagrams,
Yeah.
and you're basically checking that Like the optical theorem works?
Well, not really, right? Because as you said, this is a pole, and this is a cut of some infinite sum. I don't know. And to write these dispersion relations, we have to assume some crossing, some sub-exponentiality. This resummation of diagrams is not crossing symmetric. It does not obey all these properties. So it's really we use these general things, and it all, well, maybe it's not surprising, but all these basic principles, they're consistent, and the factor comes out right.
Sorry, one more question. Maybe I misunderstood, but this meeting in this last check, was it important or not? Or,
sorry, that's what?
This meeting is in this check that you made.
No, there was no smearing. There was no smearing. Now, I think from maybe, so you can be more careful. Here, I use this, in the first lecture I said, well, the conjecture is based on the pictures that we know exactly the radial limit of this amplitude, which is given by a conal saddle, because everything else decouples. I use this check. You can be less aggressive, and you can say, I don't know what the radial limit is, let me use this to derive a bound on the radial limit. And then you can write this Tauberian theorem, but to derive Tauberian theorem, you want this guy to be non-negative, otherwise you cannot derive a theorem. And for this guy to be non-negative, you have to do the smearing. So if you do the smearing, then you can write a Tauberian theorem. And I think that's what Leonardo and friends been doing, but here I'm doing something, in a sense, simpler. I'm saying, okay, we have a guess for what it is, so we can just check. Yeah. I think there is a mic behind you.
It's a bit of a stupid question, but the fact that the space-time d-dependence cancels, is it trivial or is it non-trivial?
No, it's not trivial. You have lots of gamma functions, but they all cancel. So.
But it depends on the form of the phase shift, not just on kinematics.
Oh, yeah, it depends on the form of the phase shift, and there is a gamma function inside the sine square, so yeah.
Thanks.
It is not trivial, yeah.
So, I don't know, to get a sense of how strong this check is, are there modifications of gravity for which it fails?
Not that I know, because this is really IR. So, at least in all consistent theories, we know in string theory it will work, also we expect. I think this is completely general because, okay, let me be again maybe more conservative. Let's say you cook up a theory, something maybe like a Vasiliev theory, where it's incredibly non-local, and I don't know, geometry is such that this whole regime is completely not classical GR. I think then it's all wrong. So in some sense, I do assume that I have a classical GR, some heavy stuff, and then it works. But then again, you can say, well, maybe I have some very exotic objects whose size grow with energy very fast. They completely spoil all this picture. Okay, but this seems to me a wild scenario. But maybe sometimes it's realized. Yeah. Okay. So this was this check, and one last comment that yeah.
This is in the same footing as these checks that people do in the usual Bootstrap, finding a singularity in the T channel as a sum of this analytic Bootstrap.
I think it's slightly different. So let me explain what the difference is. So in the usual Bootstrap, what you do is that you take identity on the channel in one channel, and you say the high energy should be that, right? That's the usual story, Cardi formula. And this would be what if I do, if I take this pole as my input, I smear it, I derive a formula, I derive a prediction. Here, it seems to me the non-trivial part is that both the pole and the radii are controlled by semi-classical computation. And this is something special about gravity. We do not have such thing in QCD. You know, in QCD there will be a similar equation, but there we have no idea what this is. The miracle here was that the classical theory was such that it allows us to compute the radial limit. And the classical theory a priori didn't know anything about this dispersion relation. When you compute the propagation through a shock wave, all the results that we got, they were only valid here. For example, if you take the saddle, try to continue it, as you know, it's not crossing symmetric. But if you assume there is an underlying crossing symmetric amplitude, which satisfies all that, you derive this equation, And then in this equation, the only input you need is a Regge limit on the real axis. And this you can use using iconal. So that's, I think, a difference compared to the usual Cardi formula, that there is an independent computation for the right-hand side. But again, yes, so, well, but you see that again, yes, I agree, you can do that, but then how do you know that this has, this is a computation of an amplitude in some limit, which perhaps is correct, but all these steps, and if you take the computation this limit, it does not satisfy crossing, it does not satisfy this sub-exponentiality. So this is a bootstrap assumption that there is some non-perturbative object behind from which this computation captures a certain limit. And these assumptions were put in deriving these equations. They do not follow from resumming diagrams or perturbative computations. So, and also when we were deriving twice subtracted dispersion relation, we use non-perturbative unitarity, which is again something non-perturbative. So there were several non-perturbative steps on the way which are not part of this computation in semi-classical GR. I don't know, Pedro, if it answers your question.
If you just look at the iconal amplitude
Yeah.
by itself, just take it as a mathematical formula, could you just blindly apply some sort of contour integral to it, or
No,
it just doesn't work?
no, you cannot.
So
No,
it doesn't
no,
work.
it doesn't work.
So in a sense, this check then shows that perhaps this iconal amplitude allows to be continued into
Exactly,
this region.
exactly.
Okay,
So-
then it's not trivial.
Sorry?
Then it's not trivial.
Yeah, it is non-trivial in that sense. And in fact, it's an open, in a sense, it's an open, as far as I know, it's an open problem to cook up an amplitude, which is a fully crossing symmetric and has both iconal and a pole. So perhaps it's possible. It has not been done. But here we're just doing some consistency check. So. And again, yes, the key thing compared to the usual Cardi is that this is computable within a semi-classical GR. Yes, and as
The result is the same as if you were just resumming right?
for this guy.
Yes.
Yes, for this guy, it's the same as letters. Yeah, yeah. But you cannot use this result to derive this equation. To derive this equation, you have to assume there is some other object which becomes some of these letters and some limit, and this object satisfies the usual bootstrap axioms. If you just resum the letters, you will not get this equation. Yeah. Yes, and as I mentioned, one open problem for Bootstrap is to here we use SU crossing, but in principle there is addition ST crossing. So find an amplitude which satisfy crossing plus iconal. Or because if we can consistently construct this class of amplitudes, this seems that this is a relevant space for gravitational amplitudes. Okay, any other questions? Now I want to make next comment because I feel it's sometimes stated in a confusing way in the literature, so I just want to quickly discuss this, which is that the lower bound on scattering, well, let me call it like this, the Cyrillus Martin bound. So there is this thing in the literature called sometimes lower bound on scattering at fixed angles. It is not a lower bound on scattering at fixed angles. That's what I would like to say. So usually you might have seen it in the context of QFT. you might have seen this formula that T s theta should be larger or equal at large energies as E minus S log S, sorry, square root log S, f of theta. This is what Serlers and Martin showed under some assumptions. And in QFT, and sometimes people, when discuss gravity, as I told you, there is a conjecture or that this behaves like e to the minus s of the black hole, and if you recover the powers of s, you get e to the minus square root s 1 plus 1 over d minus 3. So the amplitude, if you believe it's e to the minus black hole, it decreases strictly faster than this bound. So if you believe this formula, it violates this bound. So what is this bound? This bound is not, in fact, derived in QFT. It's derived... Yes, yeah, sorry. Thank you. F of theta, so it's not the same f. Yeah, the important factor is it's larger than 1. Yeah. So it violates this thing. What does it mean for gravity if it means anything? So I just want to quickly remind you how this bound was derived. So what goes on to this bound is maximal analyticity. And Mandelstam representation, if you wish. And by Mandelstam representation, I mean that this guy is polynomially bounded for any t on the principal sheet. So it's not just, sometimes in derivation of a Mandelstam representation, you have to go to unphysical t's, which can be positive and large, and you still claim that the amplitude is bounded by a polynomial. This is an essential ingredient of this proof. So it's not a proof in QFT. It's proof under these larger assumptions. And one way to state it...
Sorry, Sasha. So the prefactor here is just the amplitude at some point, right? The amplitude can also be 0. So
yeah. So you have to. I think. Well, if you assume maximal analyticity, and you have it could be that it's 0 here, but let me derive it. What the formula is, and. So the meaning of the formula is rather not that it's a lower bound on a fixed angle scattering. It's rather that Regge limit is bounded by fixed angle times Mandelstam with some prefactors. And so roughly what Serlers and Martin did, they say, well, Regge is bounded by power, Mandelstam is bounded by power by assumption, therefore we divide by Mandelstam, so we get the fixed angle as larger than something. And the way it works is that you look at the z-plane, and you consider three regions. Sorry. Okay, sorry. I will explain the following. So this formula, which follows from maximal analyticity and the Mandelstam representation, which I will now try to derive, tells you that if you take an amplitude in the Regge limit, then it is bounded by the product of the formula in the fixed angle scattering. It's all high energy, times a Mandelstam. Mandelstam means T can be very large. So Mandelstam means it's this unphysical T's, which could be positive of order S or complex. But you assume that for Mandelstam representation, all these guys are bounded by power. And so then, if you just use a simple theorem in complex analysis from these two, It is, well, it is Schwartz-like. Well, let me write just a derivation. At least it follows from this Hadamard's three-circle theorem. The Hadamard's three-circle theorem tells you that if you have an analytic function and you have, let's say, a circle of radius 1, a circle of radius R2, and a circle of radius R3, and the function is analytic, and you define by M maximum of the function on a given circle, so let's say you have some F. Then you have the following inequality, MR2 less or equal than M1, let's say M1, 1 minus log R2 over log R3 times MR3 log R2 divided by log R3. So this is a theorem. And then what you do is that you just do a complex transformation which maps this circle to, so you have one circle mapped at fixed angles, the second map to the radial limit, and the third maps to the Mandelstam. So this you map to fixed angles. This you map to Regge, and this you map to Mandelstam. And the map, the way, and so this formula become Regge is bounded by a product of fixed angle times a Mandelstam, and in the familiar, if you do the z plane where z is a cos theta, so you have minus 1, 1. So you take the region which is just like this, a pancake. That's your first circle. Then, well, sorry. You can take some region of finite angles. This is your first circle. Then you take some type of region which looks like this, which comes very close to theta equals 0. This becomes a radial limit. And the third you take to be this circle which goes into far in the complex plane. And then there is a specific complex. This doesn't look very convincing. So there is a, sorry, Pedro, but there is a specific transformation which I can show you, which maps this picture into 3 circles. And then you apply this theorem, and this becomes this bound. So in fact, the Serulus-Martin bound says that if your amplitude satisfies maximum elasticity and Mandelstam representation, it cannot decay faster than that. Or, in other words, another way to state it, if you believe in this formula for gravity, then there is no, then you can say that Mandelstam, there is no Mandelstam representation in gravity. So that's I think it's a more reasonable way to read this bound. It's not a lower bound. It's not a lower bound on anything. It's just a test if our theory admits a Mandelstam representation or not. And here, if we violate it, it simply means that perhaps we can drop this assumption, and then we are completely fine. So because sometimes people say that this is a violation of locality in QFT, in gravity. Okay, I'm not sure what it means. Tree-level stringy amplitude violate this and violate that, because for tree-level string you get e to the minus s. Okay. Next, I want to continue filling this picture and go a little bit less universal. Oh, I have to finish right soon. 10 minutes, okay. So next, I want to discuss this was completely general, but I think that's it, as far as we can go without making any further assumptions. So if we want to make further progress, we need to say something. And so, well, there is one available UV completion of gravity in flat space, which is string theory. So let's describe stringy features of this picture. And we will do as let's assume, as usual, the interesting regime, or maybe that's the regime we want to consider. M string is much less than M Planck. And remember that in string theory, so it's this G Newton, he related to the string coupling as follows: GS square ms d minus 2 times some numerical prefactor. And if we introduce this new scale in the theory, which we of course think of as a scale of some non-locality, then you imagine that there is a limit. For example, there is a limit. Oh, I have to go far. Okay, maybe I'll not go there. Basically, that some of the things we said do not hold. And one natural scale that we have to consider is the correspondence point. The correspondence point and this is the point, this is some energy, S star, at which the Schwarzschild radius is equal to string length. Here, Ls is 1 over ms. Because you expect that if your Schwarzschild radius becomes less of a string scale, then you cannot form a black hole anymore, and all this black hole physics perhaps becomes irrelevant just because you never, the basic argument, you take lots of energy, you put it inside the Schwarzschild radius, you form a black hole. But if the Schwarzschild radius becomes stringy, this argument does not make sense anymore because the objects are non-local already. And if you plug all the definitions, you get that this correspondence point is at M string divided by G string squared. And in this way, in string theory, and again, in the past, in the literature, whenever you have energy less than S star, and the same actually apply for B less than Ls, and we will see that it's Ls times log S, alpha prime, which is the same as Ls squared. This we can call a stringy gravity. Because the expectation is that in this regime, string effects become very important, and we have to consider them. So basically, we have this picture that we had before. So log S. Of course, if we have now here log of M string, so everything that's below MS, it's usually when we do dispersion relations, this is EFT. We know everything here. This is the usual story. But now we have this new thing here, which is log ms over g string squared. So notice that this implies, yes, that we consider that it's gs much less than 1. Usually it's weakly coupled. So this scale is far away, and we expect that there is no collapse beyond this point. So in fact, the guess, again, I'm drawing some picture. What exactly this picture means, it's up to future great papers who will clarify that, but no, this is a scale when Rs is equal to Ls, and it's not M Planck, because M Planck, let me write it here, M Planck is ms divided by g string 2 over d minus 2. So I can put M Planck here on this curve again, and because we are dividing by small number, this is larger than M Planck. So much larger than M Planck then, because here you have gs2 over d minus 2. The idea is that somehow this collapse region is bounded here. Now here we have this region. Let me just I need to have one bigger one. We have this region, which I guess we don't know exactly what happens, but it's some kind of physics which would be interesting to understand. And I guess it was mentioned in the talk by Shi that there is this Polchinski-Horowitz string star solution, and I guess if I understand correctly, then this Polchinski-Horowitz string star is approaching this guy, this energy scale from below. Maybe she can correct me if I'm wrong. And then there is a question: what exactly happens? What is the nature of this transition? Can we solve string theory somewhere here and say something about the amplitudes, and maybe learn something about the collapse? So this is a very interesting point. So this was, I guess, maybe it's the best strategy to learn something about it. And here we were hoping to learn something about using gravity waves about this region. Now, finally, there will be another natural scale, which is ms over gs to the first power. And here, the idea would be that here that will be, in the scattering, it will be single string physics. But as you approach here, the production of strings become important. And I guess as you approach this point, at least the analysis of ACV and everything that they did breaks down. So ACV cannot approach this region, but they can say something in this region. Then here there was log B, and here I'll put again some string scale. And so the idea is that somewhere, I guess here, somewhere in this region, we have stringy gravity, which stringy regime. And so all these curves that we were drawing, we basically have to understand what happens to them as we cross to the stringy regime. So that's what I will do perhaps next. And yes, I will describe, and this was again, just to emphasize this stringy regime, I will simply review. This has been all done by ACV, so they basically uncover a few basic features. So I will simply review what these features are, and finally I hope to say also what people have been saying, or what do we know about this collapsed region, which is not much, but I will mention this as well. So maybe I'll stop here. Thanks.